So let's try some examples using gravitational acceleration. Here we go. Veronica throws a ball upwards from ground level with a speed of 20 meters per second. When is the ball 5 meters high, and how fast is it moving at that point? Okay, so where do we start? Well, let's start with drawing a picture. Again, we've got a ball tossed from ground level. So I'll draw this. Just drawing ground level. Here's a ball. It's thrown upwards. We have that it is traveling initially at 20.0 meters per second. And the question is, when is the ball 5 meters high? So we're looking for the final position to be 5 meters up from ground level. Okay, there's our picture. Let's write down our variables. Again, let's remember x naught x, v naught v, a, t. Now let's figure out, what do we know? Well, x naught, the initial position. Well, now we've got a problem that's vertical. However, there's no reason why we can't make our coordinate system upwards. So let's draw our origin. Let's put our origin at the ground, and our coordinate system will go upwards. In other words, upwards will be positive, downwards will be negative. So x naught, the initial position, well, assuming the origin is at the ground level and the ball is starting at ground level, the initial position is 0. X is the final position. Well, we're looking for when the ball is 5 meters high, so that's going to be x. So x is 5 meters. V naught, the initial velocity, well, we know that's 20 meters per second. V, that's the final velocity. Well, we don't know how fast it's moving up here. We haven't figured that out, so we don't know. A, well, we do know the acceleration. The acceleration is due to gravity, and the acceleration due to gravity is always downwards, down towards the Earth. So the acceleration is going to be 9.80 meters per second squared, but it's in the negative direction. We said upwards was going to be positive, and the acceleration is downwards, so the acceleration is going to be negative 9.80 meters per second squared. And then t, we don't know how long it takes to get there. We don't know the time. The question is, when is the ball 5 meters high? So what are we looking for? We're looking for t. And then, how fast is it moving at that point? V. What is v? So that's the question that we're looking for. Those are the terms that we're looking for. So let's look at our equations. We've got them over here. Again, go through each equation and figure out which one will get us what we want. I'll kind of jump ahead a little bit. I'm going to use equation number 3. That has got all the variables that we know except for t, so we can use that to solve for t. So what do we have? X equals x naught plus v naught t plus 1/2 a t squared. X naught, 0. V naught, we've got that. Okay, so let's put in our values. X is equal to 5 meters. V naught is equal to 20 meters per second times t plus 1/2. A is minus 9.80 meters per second squared, and then times t squared. And what we want to do is then solve this equation for t. Well, we've got a t here and a t squared over there. It looks like a quadratic equation. So let's put this in standard quadratic equation form, which is typically, usually we write a quadratic equation ax squared plus bx plus c equals 0. In other words, we want the squared term. We've got a negative sign, so I'm just going to bring that over to the left side, so it'll be positive. So I'm going to bring everything over to the left side. I've got 1/2 times 9.8, that's 4.9. So we've got 4.90 meters per second squared, t squared. That's what we get from here when we bring it over to the left side. Then minus 20.0 meters per second t plus 5 meters, and that's all going to equal 0. So here we've got a quadratic equation in the form at squared plus bt plus c equals 0. And we know the solution to that is, hope you remember your quadratic equation. This is something we're going to be using often, so make sure you remember The solution is the opposite of b plus or minus the square root of b squared minus 4ac all divided by 2a. Now be careful, a in this case means the coefficient of the t squared term, not the acceleration. So don't get this a confused with that a. So what do we have? T is equal to, now I'm going to write the solution in a slightly different way. I'm going to group some terms here. We've got minus b, okay, here's b, so that's going to be 20 meters per second, plus or minus, then b squared, 20.0 meters per second. There's a minus there, so we've got to square that. And then minus 4 times a, which is 4.9 meters per second squared, times c, which is 5 meters. We've got to take the square root of all of that. And then divide the whole thing by 2a, which is 2 times 4.90 meters per second squared. There we go. So there's the whole solution. What I'm going to do is to group this term and put the denominator over it, and then plus or minus this term over the denominator. So what do we get in that case? Well, we'll get 20 divided by 2 times 4.9. 2 times 4.9 is 9.8. So we'll take 20 divided by 9.8, and we get 2.04 meters per second divided by meters per second squared. That's like multiplying by seconds squared over meter. One of the seconds cancel, the meters cancel, and we end up with seconds, plus or minus. Then I'm going to square this, subtract that, take the square root, divide by 9.8, and that gives us 1.78 seconds. So we've got 2.04 seconds plus or minus 1.78 seconds. That's going to give us two answers, 3.82 seconds or 0.26 seconds. Now, that's very odd. Why do we have two answers to this problem? Why not just one answer? Why do we have two answers? Well, if we think about it, go back to the original statement of the problem. What's going on? We're throwing a ball from ground level, it's going up, and we're asking the mathematics to tell us at what time is it at 5 meters. Well, the fact of the matter is, it's at 5 meters at two different times. It's going to pass 5 meters once on the way up, and then once on the way down. So, it's going to pass 5 meters on the way up after only 0.26 seconds, and then it's going to go all the way up and then come back down, and it will pass 5 meters once again after 3.82 seconds. So the fact that we have two answers makes complete sense. That is completely understandable. Now, the second part was, what's the speed, or how fast is it moving when it passes that point? So what we can do is figure out the speed. We'll use the first equation. We have v is equal to v naught plus at. We'll put in the first velocity, the initial velocity, and the first time, 20.0 meters per second, plus a, which is negative 9.80 meters per second squared, times 0.26 seconds. Multiply that out, and we get a velocity of 17.4 meters per second. Now let's put in the second time. We have 20 meters per second plus 9.80 negative meters per second squared times 3.82 seconds. Multiply that out, and what do we get? We get negative 17.4 meters per second. So this is very interesting. After 0.26 seconds, the speed is positive 17.4 meters per second. After 3.82 seconds, the speed is negative 17.4 meters per second. So what's happening is, it's going up, and when it passes 5 meters the first time, it's still going up, so the speed is positive. On the way back down, it's coming down, and so the speed is negative, and that's exactly what we find for the two different times, and that makes complete sense. One thing to notice is that these are actually exactly opposite each other. So it's going just as fast upwards on the way up as it is on the way back down when it passes that point again. So the motion is completely symmetric up and down, giving rise to the same speed, opposite velocities, opposite signs, but the same speed as it passes that point. A very, very interesting result. Now, one last part, let's just look at one more part of this question. Let's figure out how high does the ball actually go. What's the maximum height? If we assume this ball is going up, it's going to go up to some point, turn around and come back down. How high does it go? Well, this is a different question than what we had before, so we can't use these times. The time is going to be somewhere in between these times. Well, what is significant about the highest point? The highest point occurs when the velocity is actually 0. So an object is at its highest point when it actually is momentarily at rest. It stops at the highest point and then turns around and comes down. So the velocity is positive, 0 at the highest point, and then negative on the way back down. So let's figure out where is the velocity actually 0. So let's come over here. Let's assume then that our final velocity is 0. How high is it at that point? Well, what we can do now is use the fourth equation. Let's assume that the final velocity is 0. We have v squared equals v naught squared plus 2ax minus x naught. X naught is 0, and now we're going to set our final velocity equal to 0. And what we want to do is solve for x. So we'll bring v naught squared over here, divide by 2a, and what we have is x is equal to minus v naught squared over 2a, or negative v naught is 20 meters per second squared divided by 2 times a is negative 9.8 meters per second squared. Notice we have a negative and a negative, which cancel, giving rise to a positive value for x, which is what we would expect, a positive value for the final position. Put these numbers in, and what do we find? X is equal to 20.4 meters. There we go. So we figure out just exactly how high the ball will go before coming to rest. All right, very good. Let's try one more problem. Go ahead. Okay, so one more problem. While visiting the top of the Washington Monument, which is 427 meters tall, Io notices her physics professor on the ground below. Io tries to get his attention by dropping a rock on his head. How long will it take the rock to fall, and how fast will it be moving when it hits his head? Assume Io's professor is 2 meters tall and ignore air resistance. Okay, there we go. So, let's start off by drawing a picture. We've got the Washington Monument, which is, 427 meters tall. You've got a rock dropped from the top of the Washington Monument. It's going to hit an unfortunate physics professor on the top of the head, who is 2 meters tall. We'll assume the rock is dropped. In other words, it's not thrown down. So if it's dropped, we're assuming the initial velocity is what? Well, if it's dropped, we'll assume it's 0. So what do we have? We're going to use this is a vertical problem again. So we'll define our x-coordinate vertically. We can put the origin anywhere we want. Let's put the origin, say, down at ground level. So here's the origin. And our x-axis, let's say, upward is positive again. Okay, so what are the variables? Again, as usual, x naught x, v naught v, a, t. What values do we have? X naught, the initial height of the ball, or the rock in this case. So the rock was 427 meters above the origin. So x naught in this case is now 427 meters. X is what? The final height of the rock. The rock hits the physics professor on the head. So the final height is 2 meters. V naught, the initial velocity, assuming it's dropped from rest, so V naught is 0. V, the velocity down here, we don't know what that is. A, the acceleration, ignoring air resistance, the acceleration is only due to gravity. Again, the acceleration is downward, which is going to be in the negative direction since we defined upward as positive. So A is negative 9.80 meters per second squared. T, we don't know what that is. So that's it. The question is, how long will it take the rock to fall, and how fast will it be moving when it hits his head? So what are we looking for? How long will it take? We're looking for T. How fast is it? We're looking for V. There we go. So we've got the variables that we know, the ones we don't know. Those are what we're looking for. Again, back to the equations. So let's find how fast it's moving. Let's find V to begin with. What do we have? Can we use number 1? No, we don't know the time. Can we use number 2? No, we don't know the time. Number 3, don't know the time. Doesn't even have a V in it. We'll use number 4. So what do we have? V squared equals V naught squared plus 2a x minus x naught. V naught is 0. So what do we have? V squared is equal to 2a x minus x naught, or V squared is equal to 2 times a, negative 9.80 meters per second squared, times x, which is 2 minus x naught, which is 427 meters. 2 minus 427 is negative 425. That negative, along with this negative, makes it positive, so the product of the right-hand side will be positive. We take the square root to find V. What we find is V is equal to plus or minus 91.3 meters per second. We take the square root of a number, it could be positive or negative. Well, which one do we want? Do we want positive or negative? Well, thinking about the problem here, the rock is coming downwards. When it hits the professor on the head, it's going to be moving downward. We actually want the negative answer. We want the answer where the motion is downward. What does that positive mean? Does it have a meaning? Why is there a positive answer if it doesn't fit with our problem? Well, the fact is that actually it does fit with the problem, just not with the physical nature of the problem. If we could imagine this rock as dropping down from the top and then finally hitting the professor on the head down here at 2 meters, what might that rock have been doing at an earlier time? Well, obviously, physically, we know that perhaps Io had the rock in her pocket or she picked it up off the ground or whatever. However, the mathematics doesn't know anything about that. The mathematics thinks the rock is still moving with a uniform acceleration. In other words, the mathematics thinks the rock is still only acting under the influence of gravity. Well, what might a rock have been doing prior to t equals 0 if it was only moving under the influence of gravity but ended up here at t equals 0? Well, we could imagine that it might have been moving upwards, reaching its peak up at the top and then falling back down. And so the fact is, if we kind of imagine something like that, it could have been at this height, at 2 meters, prior to the point that it was dropped, where it would have been moving upwards. Exactly like the previous problem, a symmetric sort of problem where it's moving upwards and coming back down, and so we actually could have had it moving at plus or minus 91.3 meters per second and being at 2 meters height. Now, obviously in this problem, only the negative velocity is suitable for our problem, so we don't need to worry about the positive, but it's good to understand why we actually get those two solutions and what that actually could mean. So, assuming that our velocity is negative 91.3 meters, that's the answer to the part of how fast is it moving. At what time is it? Well, now we can go back to our equations. Now, what equation shall we use to solve for the time? We could use equation number 3. In that case, it is again a quadratic equation in terms of t, for which we'll get two solutions. Similar to the previous problem, we'll get a positive time solution and a negative time solution. We know in this case we only want the positive time solution. I'm actually going to cheat a little bit from what I told you before. Why don't we just use equation number 1 and use the velocity that we've solved for. That will give us just one single value for time. It'll be a little bit easier than solving the quadratic. So let's jump and use equation number 1. We have v is equal to v naught plus at. V naught is 0, and so t is going to be v divided by a. Very simple to solve. V is negative 91.3 meters per second divided by a, negative 9.80 meters per second squared. Meters cancel, bring second squared in the denominator. From inverse second squared, bring it up, that makes it second squared, cancels one of the seconds, we end up with the time in seconds, and the answer turns out to be 9.31 seconds and positive. There we go. There is our final answer. So we get our final velocity is negative because the rock is moving down. The time is positive because it occurs after the rock has been dropped, and those certainly seem like reasonable answers, particularly considering we've got a very, very tall monument. It's falling a very great distance. Great. So that's it for lecture number 3. Next time we will take a look at some more motions, but we'll start looking at two-dimensional motion.